1220. You are pushing a cart across the room, and the cart has wheels at the front and the back. Okay, so wheels at the front and at the back. Alright, your hands are placed on the top of the cart at the center of the top edge, pushing horizontally. Okay, so there's F contact. Okay, there is friction between the wheels and the floor. Fs. Fs. Wheels, floor. Wheels, floor. Okay. Is the normal force between, and by the way, there's also obviously F normal force between the wheels and the floor. F normal between the wheels and the floor. Is the normal force between the floor and the front wheels, let's call this the front. Okay, this is the front. Back. Greater than, smaller than, or equal to the normal force between the floor and the rear wheels? Explain your answer using an extended free body diagram. Okay, so we're almost there. We've got most of the forces. The only other one we need is what? We need the center of mass there, and we've got gravity between Earth and the cart. Okay, so those are all our forces acting on the cart. Alright, I hope you can get this. So they're asking, is this normal force greater than, equal to, or smaller than that normal force? Well, we just had a bit of an idea of what's going to happen when we looked at a previous problem where we saw a car going around a bend, and we had a friction force acting towards the center of that curvature so that the car would not slide off and keep going in the same direction. And we saw, when we looked at the car from behind, we saw that the car would tend to want to tip because there's a torque, and so this one would tend to come off the ground first. So perhaps there's something similar here, and it's to do with torques. Okay, so we know that at this point the sum of the torques is 0. The sum of all the torque. Why? Because it is in rotational equilibrium. Rotational equilibrium. That means that it's not rotating. Not yet. Okay? So perhaps if you increase this force, it might begin to tip. I don't know. Okay? But the point is, right now, you're pushing it and it is moving, but it's not tipping. There's no rotation. So this is where we're working from. The sum of the torques exerted on this cart is equal to 0. So how about we take, I keep saying moments, that's how I was trained, but we take the sum of the torques about the center of mass. Okay? So we assume counterclockwise is positive. Remember, it's our assumption. So let us sum up all the torques acting about the center of mass. Okay? So we've got this FC force, FC of say hand on cart, and that's its line of action, and that would be its lever arm. Let's call it R1. R multiplied by R1. Now this is the torque caused by this force. Is it going to be positive or negative? It will be a negative because it is going in the clockwise direction. Okay, clockwise direction. What about FG? Does FG cause a torque about the center of mass? No, because there is no lever arm. The line of action of this force passes through the center of mass, so there's no yes, there's a force by gravity, but there is no torque due to gravity. Okay, what about these friction forces? Well, this one and this one are both causing clockwise rotation, right? So we can just say minus Fs Wf, and now we need a lever arm. Remember that would be our lever arm. Let's call it R2. And for argument's sake, I'm just going to say that this is one single friction force being applied on both wheels. Okay? So we've now taken account of these two, because these two are both acting in exactly the same direction, and we can just call it our friction force times that moment arm, that lever arm. Now what about this guy? Now we've also got minus Fn wheel on floor, and I'm going to call this number 1 because they have the same, or let's call it back. Okay, so this will be the one at the back. So it also, there's its moment, there's its line of action, and that would be its lever arm. We can call that R3. So this normal force at the back is also causing a torque, a clockwise torque, and it is negative because it's clockwise, so it's that force multiplied by that lever arm. Now all we're left with is this guy, and we can see that this normal force, let's call it Fn wheel on floor front. Okay, you need to come up with better names. Fn wheel on the floor at the front. Now you need to multiply it by its lever arm, which is basically, if this thing is symmetrical, it will also be the same as R3, right? It will be the same magnitude. So we just call that R3 as well. And then that equals 0. So now as you can see, all of these are causing negative moments, and this is a positive moment. So I'm going to leave this as an exercise for you. If you take this entire, all these negative quantities, and you put them on that side, then we're going to have F wheel on the floor in the front, normal, equal to this entire thing, right? That entire thing, but now positive, divided by R3. So all you need to do is compare this value, the front one, to the rear one. Where is it? The back one. And you'll see that this one at the front is taking much higher load than this one at the back. Okay? So it's also, the idea also is just that there's this torque. Okay? So this is how you would, mathematically compute this. The front normal force would be much higher than, well, I don't know, much higher, but it would be higher than the back normal force. But there's also this, and all of this is causing a torque. So you can imagine, if you're causing a torque, there's a tendency to want to rotate this way. So this guy is going to come off the ground. There's a tendency for this guy to come off the ground before this guy. Okay, so this normal force is going to be lower than that one. Hope that helps. Cheers.